All right. So
just one second.
Okay.
Giovanna Obradovic will talk about minimal models for graphs-related operatic algebras. Please go ahead, Giovanna.
Okay, thank you. So let me see. Okay. All right, perfect. So first of all, good morning from Belgrade, and let me start by thanking the organizers and of course to all the participants for making this category stand up to standards even in these strange times. Of course, I'm very honored to be a part of it once again. All right, so today I would like to tell you about this paper that I wrote together with Michael Vatanin and Martin Markle, and that we find to be a very nice example of fruitfulness of mixing operator theory with convex and discrete geometry. So in this paper, we introduced the concept of minimal models for operands within the framework of operatic categories, and we constructed explicitly certain important minimal models, namely minimal models for hyperoperads governing ordinary operads, cyclic operads, and modular operads. And then, of course, according to the general philosophy, the algebras for these minimal models will describe the strongly homotopy versions of the corresponding structures. And of course, this might be compared to the classical situation of A-infinity algebras, for example, being algebras for the minimal resolution of the associative operand. And moreover, this nice combinatorial ingredient that we have for A-infinity algebras, namely the interpretation in terms of polytopes, is also present here in our framework. Okay, so the mechanism for introducing strongly homotopy structures within operatic categories is reflected by the triad of an operatic category. So this diagram here is supposed to indicate that all objects under study can always be seen as algebras over operads in a suitable operatic category. So here at level 0, we have operads for an operatic category O, whatever they might be, okay? And then at level -1, we have algebras for these operads. But it turns out that O operads themselves can be seen as algebras, namely as algebras for the terminal operad in the plus construction of O, which is an operatic category that we put at level 1. And this triad can, in fact, be continued upwards to infinity. And once you have encoded your O operads as algebras, you get the strongly homotopy version of your O operads as algebras for the minimal model of this terminal operad here. So a classical example of such a triad is given by the triad of the operatic category fin of finite sets. So fin operads are just ordinary classical operads, and they appear simultaneously as algebras for the terminal operad in the category of rooted trees. And the category of rooted trees is the plus construction of the category fin. As I said, once we have encoded classical operads as algebras for this terminal operad, we get strongly homotopy version as algebras for the minimal resolution of that terminal operad. Okay, another example, we have the triad of the operatic category of trees, in which cyclic operads appear as algebras for the terminal operad in that category. Once again, we get strongly homotopy cyclic operads as algebras for the minimal model of that terminal operad. And my third example is the triad of the operatic category of genus graded graphs. Here, of course, we find modular operads again as algebras for the corresponding terminal operad. All right, so this is the setting. And once again, our goal was precisely to construct the 3 minimal models, namely the minimal models that govern strongly homotopy operads, strongly homotopy cyclic operads, and strongly homotopy modular operads. And in fact, we achieved this goal by constructing yet another minimal model that happens to be so nice so that it actually allows us to get these 3 guys almost for free. Okay, so in fact, we worked in the operatic category GRC of connected graphs. So this category lies between the category of trees and the category of genus graded graphs. Concretely, the algebras for the terminal GRC operad are precisely modular operads without the genus grading. Okay, and the minimal model that we constructed explicitly was precisely the minimal model for that terminal operad. Now, the proof that this guy here, this DG operad, is indeed the minimal model of the starting terminal operad, meaning in particular that it has the same homological properties as the starting operad. So the homology of MGRC should vanish in positive degrees. The proof of that particular fact was a combination of the following two things. Okay, so first of all, we described the arity gamma space of operations of our minimal model in terms of an abstract combinatorial polytope. So to each graph gamma, we associated a hypergraph H gamma, and to that hypergraph, we associated an abstract polytope in such a way that the operations of arity gamma indeed correspond to the faces of that abstract polytope. Once we had represented our minimal model in terms of an abstract combinatorial polytope, we then showed that the genuine convex polytope that realizes our abstract polytope can be oriented in such a way that the associated cellular Che complex is isomorphic as a DG vector space to our minimal model. And of course, since this is a chain complex of a genuine convex polytope, it's acyclic in positive dimension. So of course, the same must be true for our minimal model. All right, so as I said, once we know how this guy looks like, we get these three guys almost for free, namely the three operatic categories of interest are obtained from GRC by iterated discrete operatic fibrations and off fibrations. And we show in our paper that these maps transfer minimal models. Okay, so these are the contents of our paper. And today I would just like to go through the first item and to describe this nice idea of representing this ugly DG operad in a very tangible geometric way. Okay, so as I said, we will be working in the operatic category of connected graphs. So the objects of our category are connected graphs, like this one. So some indexing is also involved here, but this is less important now. Okay, so these are our objects, and then the morphisms will be given by contractions of subgraphs. So here you can see one such morphism. So F contracts the subgraph determined by the edges U, V, and Z, and you can see by contracting U and V, these edges X and Y actually turn into loops. Okay, and then the fibers of a morphism are given precisely by those subgraphs that got contracted to a vertex. So here concretely F has a single fiber, a unique fiber, and this is precisely the subgraph that I just mentioned. Okay, so this is our category, and then by an operad in this category, you should think of it as a generalization of the classical notion of an operad, for which the arities are given by graphs and not by natural numbers. Okay, so we have a pre-sheaf M, which associates to each graph a vector space. And then for each morphism F, like this one, we have the induced operatic composition circle F. So the type of circle F should be thought of as the insertion of this fiber into this vertex here in order to recover the starting graph. And then, of course, the terminal operad in this category is the operad for which the operations of the space of operations of arity gamma is the ground field for each gamma, and of course, whose operatic composition is given by this canonical isomorphism. And it is not difficult to show that the algebras for this terminal operad are modular operads without the genus grading. And once we have encoded our modular operads as algebras for this terminal operad, we can introduce strongly homotopy modular operads as algebras for the minimal model of that terminal operad. So by definition, MGRC is the quasi-free operad whose differential has no constant in linear terms, equipped with a weak equivalence in the model category of chain complexes. Okay, so let me now show you the definition of MGRC. Here it is. So first of all, in order to define the generating collection D on a graph gamma, we're going to consider the vector space spanned by all the edges of gamma, and we're going to associate to that vector space the top dimensional piece of its exterior algebra. So this here is the one-dimensional vector space spanned by the exterior product of all the edges of gamma, okay? And then the differential on such an exterior product will be given as the sum over all possible ways to represent the graph gamma as a nesting of two graphs. So here the notation means that we have nested the graph gamma t into a vertex of the graph gamma b. And each such nesting splits the exterior product in two. So the exterior product on the left from the tensor will contain all the edges from the bottom graph gamma b, and the exterior product on the right from the tensor will contain all the edges from gamma t. And finally, the witnessing quasi-isomorphism rho will be defined as the unique map whose restriction on the generating collection is trivial for gammas that have at least two edges, while for gammas that have exactly one internal edge, in which case this space D of gamma is canonically isomorphic to the ground field, we take rho to be precisely that canonical isomorphism. Okay, so this is our main theorem. And the most difficult thing to prove here is that MGRC has the same homological properties as 1GRC. So in particular, that its homology vanishes in positive degrees. And this is where we turn to convex and discrete geometry. So by showing that MGRC admits a very nice presentation in terms of polytopes, we get this homology for free. Okay, so the family of polytopes that we shall consider is called, they are called hypergraph polytopes, and geometrically they may be characterized as truncated simplices in arbitrary dimension. So for example, in dimension 3, we start from the tetrahedron, and we are allowed to truncate its vertices and its edges. And by successfully making these truncations, we reach the permutohedron as the limit case for which all the truncations have been made. Okay, and then the polytopes in this interval of truncations from simplex to permutohedron are called hypergraph polytopes because actually each one of them is encoded by a hypergraph whose hyperedges correspond precisely to the truncations of the simplex that were needed in order to get the polytop in question. So now, before I explain you how this truncation business works, I would like to just recall a bit of hypergraph terminology. Okay, so a hypergraph is just a generalization of a graph for which an edge can relate an arbitrary number of vertices. So you generalize the notion of an edge to the notion of a hyperedge, okay? And here is a very simple example. So here we have a hypergraph on the vertex set x, y, u, and v. And then as hyperedges, we have first the 4 singleton hyperedges corresponding to the 4 vertices. And then we have 4 hyperedges of cardinality 2. Of course, these are just the edges in the usual sense. And then we have one more hyperedge of cardinality 3, x, u, v, and we can represent this hyperedge by circling out this area around x, u, and v. So this is a hypergraph. And then in order to truncate, we shall use one property of hypergraphs, and that's the property of being saturated. So we say that a hypergraph is saturated whenever for any two of its hyperedges, x and y, holds that if x and y have a non-empty intersection, then their union is also a hyperedge of that hypergraph. And if you go back to our example, you can easily see that H is not saturated. For example, the hyperedges x, u, and x, y have a non-empty intersection. Obviously, their union is not there as a hypergraph. But of course, given any hypergraph, you can saturate it precisely by adding all those missing unions of edges, of hyperedges. And in this concrete case, we saturate our hypergraph by adding these 3 guys. All right, so now, given a hypergraph like this one, how do we obtain its corresponding polytope? So let me show you that. We still have the same hypergraph as before. First of all, the starting simplex, so the simplex that we shall truncate, will be the simplex whose set of facets corresponds to the set of vertices of my hypergraph. So here our hypergraph is defined on a 4-vertex set, and this is why we start from with the tetrahedron, okay? And I'm going to label the facets of the tetrahedron by the names of those vertices. So here the triangle on the left is x, the right one is u, the back one is v, and the bottom one is y. So this is the starting simplex. And then the instruction for truncation is read from the saturation of my hypergraph, namely each hyperedge of the saturation of arity 2, of cardinality, sorry, 2 and 3. So these guys, each of them will correspond to one truncation in the following way. So for example, this guy XUV tells me to truncate the face of the simplex defined as the intersection of face sets XU and V. And of course, this is the top vertex here. So I truncate. And then, of course, these two guys will give me two more truncations of vertices, this one and this one. And now you may guess that these four hyperedges of cardinality 2 will correspond to truncations of the edges of the simplex. So I truncate. Okay. So that's it. The idea is rather simple. The polytope we obtained is called the hemiisosahedron. And in our paper, we give the actual combinatorial description of such a polytope. So we show how to derive the face lattice from the data of the hypergraph. Okay, so now if we are okay with hypergraph polytopes, let me show you how we demystified and proved our main theorem. So the demystification lies in the fact that the operations of the arity gamma of our minimal model correspond to the faces of the hypergraph polytope, whose hypergraph H gamma is associated to the starting graph gamma in the following way. So the vertices of my hypergraph will be the edges of gamma. Okay, so we have X, Y, U, and V. And then two vertices in the hypergraph will be connected by an edge whenever, as edges of gamma, they share a common vertex. Okay, so starting from a graph gamma like this one, we build the hypergraph H gamma in this way, and then we prove that the faces of the corresponding hypergraph polytope actually correspond to the elements of the free operad that defines our minimal model. Okay, so at this point we have the first half of the proof of our main theorem. So we managed to describe our minimal model in terms of a combinatorial of an abstract polytope. Okay, of course, once you have this description of the arity gamma space of operations, the rest of the structure of MGRC carries over easily. So the composition of the operad should be thought of as the Cartesian product of faces, and of course, the differential of MGRC will be just the boundary operator. Okay. At this point, what remains to be done is to show that the genuine convex polytope that realizes this abstract polytope can be oriented in such a way that the associated cellular chain complex is precisely our minimal model, which is a pretty clever way to obtain its homology. And this is precisely what the ingenious lemma says. Okay, so the lemma says that the faces of the genuine convex polytope that realizes our abstract polytope can be oriented so that our minimal model is the cellular chain complex of free abelian group generated by the faces of the realization, and whose differential on an oriented face lambda is given as the sum of all deltas covered by lambda multiplied by 1 if the orientation of delta agrees with the orientation of lambda, and multiplied by -1 otherwise. So here just a comment on the notion of orientation. So we say that a face of a polytope lambda is oriented if we have chosen a frame in the affine space A lambda of lambda, okay? And then if delta is a codimension 1 subspace of lambda, we say that delta is oriented compatibly with lambda if the frame that determines the orientation of delta extended with the vector normal to that affine space, which moreover belongs to our polytope, determines the orientation of lambda. All right, so this lemma is proven by induction on the dimension of faces, downward induction, okay? So we start by choosing an arbitrary orientation of the top dimensional face, okay? Of course, we assume that we have oriented all the faces of dimension k and greater, and we pick a k-1 dimensional face A, so we want to orient A as well. How we do that? Well, we pick a face E that covers A, And we look at what happens in the differential of E precisely here in the combinatorial description of our minimal model. Of course, we can do that because this is the realization of the polytopes that appear here. So if A occurs in the derivative of E with the plus sign, we give it the orientation compatible with the orientation of E. Otherwise, we give it the opposite orientation. So you can see that this receipt really forces the differential of the associated cellular chain complex to act in exactly the same way as the differential of our minimal model. So there is really nothing deep happening here, but actually the trick here is to show that this receipt does not depend on the choice of this phase E here. And we prove that thanks to a very nice property, which we show to be satisfied by our realization. So we call the property the diamond property. And the property says that precisely that if a phase A is covered by two phases, E prime and E second, then there exists a phase H that contains E prime and E second in its boundary, okay? It sounds very simple, but actually this is not satisfied by an arbitrary convex polytop. So by invoking the diamond property, if we imagine that A is covered both by E prime and E second, we pick this phase A, which is promised to us. We apply the square of the differential to H. Since the differential squares to 0, this will give us an equality involving various signs. And then by analyzing this equality, we see that the orientation that is given to A from E prime must always be the same as the orientation given to A from E second. Okay, so to summarize, the ingenious lemma tells that our minimal model is the cellular chain complex of a genuine convex polytop, which of course means that it's acyclic in positive dimension. Okay, so if you're interested in the details of these constructions, in particular, if you want to see how this minimal model transfers to minimal models of other categories of graphs, you can find the details in our paper. So that's it. Thank you. Okay.
Thank you very much, Giovanna. Do we have questions for her here in the audience first? How does it look online? Questions? I just have the comment that I was really grateful that you brought the abstract theory to life through amazing graphics. It was wonderful. Thank you. No questions? All right, then let's thank Giovanna again for the talk.